Every single day, this city somehow keeps more than 8 million people alive. It's a daily miracle of logistics and engineering, a complex dance of systems operating on a scale that's almost impossible to comprehend. More than 1 billion gallons of water delivered, 11 million megawatt-hours of electricity consumed, and 66,000 tons of waste and recyclables removed. All of it happens around the clock, mostly out of sight, and almost nobody knows how. We take for granted that when we turn on a tap, clean water will flow. We assume the subway will arrive, the lights will turn on, and our digital world will connect. But behind these simple actions lies a hidden world of immense complexity. Where does New York get its drinking water, and how does it travel 100 miles to reach a fifth-floor apartment? How does a century-old subway system move millions without grinding to a halt? What happens beneath the streets every minute to keep the city breathing? To understand how New York survives today, we have to start with why it exists at all. The answer isn't found in steel or concrete, but in water and rock. Long before it was a city, it was a perfect natural harbor, carved by glaciers during the last ice age. This process created a deep, sheltered anchorage in the Hudson River, not just a river but a tidal estuary, an arm of the sea reaching deep inland. This unique geography made inland trade possible on an unprecedented scale. Then, in 1825, human ambition amplified this geographic advantage. The opening of the Erie Canal created a water highway connecting the Atlantic to the Great Lakes, funneling the vast resources of a continent through this one port. Goods and people flowed faster and cheaper here than almost anywhere else in America. Geography chose New York. The sheltered harbor, the deep water access for the world's largest ships, and the river network linking the ocean to the heart of the continent. It was a recipe for a global crossroads. Commerce exploded, which in turn attracted finance. Waves of immigration provided the labor. Industry followed, and with it, a relentless cycle of growth. Each layer multiplied the city's density and its ambition, creating problems of a scale never seen before. How do you house millions on a narrow island? How do you build ever higher? The answer, once again, was hidden in the ground. Crucially, an incredibly hard, stable rock called Manhattan schist sits just below the surface. This ancient metamorphic rock is the city's secret weapon for building tall. It's strong enough to support the immense weight of a skyscraper without shifting or compressing. Think of the bedrock as a giant, immovable handle. Instead of floating on soil, builders could excavate down to this solid anchor and bolt their towers directly to the island itself, creating a foundation as stable as the continent. But a city is more than land and buildings. It is a living machine, a network of arteries and nerves for moving people, water, power, information, and waste, every hour without fail. This machine is what transforms a dense collection of structures into a functioning metropolis. To see how this machine was built and how it works, you have to start with its first and most important blueprint, the 1811 Commissioner's Plan, the simple, relentless grid. It was a radical vision that treated the island's natural landscape as a blank slate, imposing a rational order that would dictate the city's growth for the next 2 centuries and provide the framework for every system to come. Before the skyline, before the city we know, there was a plan. In 1811, a group of commissioners laid out a vision for Manhattan that was as audacious as it was simple. Surveyors, led by the meticulous John Randall Jr., took this radical idea and drew it directly onto the island's blank hills, forests, and swamps. The concept was a relentless, rational grid. It was a declaration of intent, a city built not on history or topography, but on the principles of commerce and expansion. This wasn't an evolution, it was an imposition, a man-made geometry laid over the natural world. The logic was brutally efficient: 12 wide avenues running north-south, 155 narrower streets running east-west, and most controversially, numbers instead of names. This was a stark departure from the winding named streets of European capitals and even downtown Manhattan. It was a system designed for strangers, for immigrants, for a constant influx of people who needed to find their way. It prioritized efficiency over romance, clarity over character. The impact was immediate and profound. The grid standardized blocks into predictable, sellable parcels of land, which fueled a real estate boom and sped up construction at an unprecedented rate. For developers and builders, it created a repeatable template. For citizens, it made navigation brain-dead simple. You don't need a map if you can count. But the grid's true genius lies beneath the surface. The regular, straight blocks created perfect channels for the city's lifelines. It optimized light and air for the buildings above, and for the engineers below, it was a gift. Threading utilities like water mains, gas lines, electrical conduits, and now, fiber optic cables, became a straightforward task. The surface grid is mirrored by a subterranean grid, a hidden circulatory system that keeps the city alive. On the surface, the grid's design channels movement with a similar logic. The wider avenues act as pressure relief valves, designed to handle the primary volume of traffic. They are long north-south corridors that absorb flows like powerful rivers, moving the bulk of the city's people and goods. But a perfectly rigid system is brittle. Manhattan's grid has a crucial element of chaos: Broadway, an older path, a Native American trail that refused to be erased. It slices diagonally across the grid. Where this diagonal line collides with the rigid geometry of the avenues and streets, it creates friction, complexity, and opportunity. Those collisions birthed iconic, triangular flatiron buildings and, more importantly, public squares. Spaces like Times Square and Herald Square are the accidental offspring of this geometric conflict. They are moments of useful chaos that break the relentless monotony, creating natural gathering places that spread and slow foot traffic. They are the exceptions that prove the rule, adding a vital, human element to the grid's cold logic. Today, managing flow on this 200-year-old grid is a high-tech science. The city's adaptive traffic control system is the grid's digital brain. Thousands of sensors, video cameras, radar, in-pavement loops feed real-time data on traffic volume and speed into a central hub. Sophisticated algorithms then choreograph thousands of signals, constantly adjusting timing plans to keep the river of traffic moving as smoothly as possible. The result is the elusive green wave. It's like catching the perfect tide. Hit the right speed on a major avenue, and the system will anticipate your arrival, turning lights green just as you approach. It's a small, satisfying moment where you feel the entire city's machinery working in concert to carry you forward. The modern grid isn't just one flow, but many, layered on top of each other. To reduce friction, the space is meticulously carved into dedicated channels, bus lanes to prioritize mass transit, protected bike lanes for cyclists, designated routes for trucks, and sidewalks for walkers. Each layer moves at its own pace by its own rules. Even the curbs, the final frontier of street space, are now programmed. They are no longer just for parking. They are dynamic micro-hubs with specific loading windows for deliveries, rideshare pickup zones, and outdoor dining. Sensors monitor occupancy to manage demand and keep these vital arteries from getting clogged by double-parked vehicles. Ultimately, for a city this dense, the goal isn't individual speed, it's collective throughput. The system isn't optimized for one car to get across town as fast as possible. It's optimized to move the most people per minute, safely and efficiently, whether by foot, bike, bus, or train. But the story of flow in New York City, the fundamental system that makes everything else possible, doesn't start on a street or in a subway. It starts long before, in a place far from the grid. It starts with water, with the force of gravity, the geology of distant mountains, and a 100-mile promise made to a thirsty city. New York City's tap water doesn't come from the Hudson or the East River. It comes from the mountains. Over a century ago, with the city's population booming and local water sources dangerously polluted, engineers looked north. They identified a vast, pristine wilderness as the solution, the Catskill and Delaware watersheds, sprawling over nearly 2,000 square miles. This decision set in motion one of the most ambitious civil engineering projects in human history. The city began acquiring huge tracts of land, not just for reservoirs, but to preserve the forests themselves, recognizing them as the first and most important filter in a system designed to serve millions. Today, this protected ecosystem does the heavy lifting. Rain and snow gather in these forests, percolating through layers of soil and rock that naturally purify it. The water then flows through a network of streams and rivers into 19 deep reservoirs and 3 controlled lakes. Together, they can hold over 550 billion gallons. This natural filtration is so effective that New York is one of only a handful of major cities in the world with a surface water supply pure enough to be exempt from federal filtration requirements. From these reservoirs, the water's long journey to the city begins, and it's a journey powered almost entirely by a single, silent force: gravity. The aqueducts are essentially man-made underground rivers, massive tilted straws stretching over 100 miles. The Catskill and Delaware aqueducts were engineered with a precise, gentle slope, just a few feet per mile. This subtle incline is enough to pull over 1 billion gallons of water a day southward, with no pumps needed for the vast majority of its trip. It's a quiet, constant, and incredibly efficient flow. The system's greatest challenge was crossing under the Hudson River. To withstand the immense pressure, engineers had to dig deep into the bedrock, over 1,000 feet below the surface. The first pressure tunnel, City Tunnel No. 1, went into service in 1917. Tunnel No. 2 followed in 1936. For decades, these two tunnels were the city's lifelines, operating continuously without a break, but they were aging and couldn't be shut down for inspection or repair without crippling the city. That's why the city embarked on its largest capital project ever, Water Tunnel Number 3. Started in 1970, it's a modern backup and a critical piece of redundancy, finally allowing the city to service the older tunnels and secure the water supply for generations to come. Before entering the city's distribution network, the water receives its final polish. At the Catskill, Delaware UV disinfection facility, the largest of its kind in the world, powerful ultraviolet light neutralizes any potentially harmful microorganisms. A small, carefully controlled amount of chlorine is also added to protect the water as it travels through the final miles of pipe. And quality is not a matter of guesswork. The system is monitored constantly with robotic sensors and hundreds of daily water samples checked for turbidity, pH, and over 250 other variables, ensuring what comes out of the tap is safe and clean. Managing this flow is a delicate balancing act. A network of gates and shafts, controlled both remotely and by on-site operators, meters the flow between boroughs. This ensures that Manhattan taps don't sputter when the Bronx showers, maintaining consistent pressure across the entire 5-borough network. Think of the distribution system like a tree. The massive aqueducts and city tunnels are the trunk. They feed into a network of smaller, yet still enormous trunk mains running beneath the city's avenues. From there, they branch out again and again into the 6,800 miles of local water mains that run under nearly every street, eventually becoming the countless twigs that terminate at your kitchen sink. Much of this underground network is a relic of another era, made of unlined cast iron. Some pipes are over a century old. To prevent leaks and ensure reliability, the city is in a constant state of renewal, swapping out these centuries-old iron mains for stronger, cement-lined, ductile iron pipe, as it systematically replaces and adds redundancy to the grid. Throughout this journey, pressure is kept in a sweet spot. It has to be high enough to serve buildings up to about 6 stories, but gentle enough to not stress the joints and fixtures of an aging system. It's a precise hydraulic balancing act, managed 24/7. But for buildings taller than 6 floors, gravity flips. The city's pressure isn't enough to reach the top, so these buildings rely on their own pumps to send water up to the roof, where it's stored in those iconic wooden water towers. From there, simple physics takes over, feeding water down to the upper floors by gravity. These towers are elegant in their simplicity. They're essentially giant, non-pressurized toilet tanks for skyscrapers. A float inside the tank drops as water is used, opening a valve to an electric pump that refills it from the city main below. Once full, the float rises, shuts off the pump, and gravity does the rest. This provides reliable pressure for the building and acts as an on-site water reserve. The result of this century-long endeavor, from protected watershed to rooftop tank, is some of the best and most celebrated big city tap water in America, a daily miracle delivered straight from a mountain. It's a system of staggering scale, largely invisible, but where water flows, power must follow, quietly, massively, every second, to keep the city alive. Ashokan, Rondout, Cannonsville, Pacton, giant batteries of fresh water, whole valleys were bought, cleared and flooded to secure a dependable supply. Forested watersheds act as natural filters, soil and roots clean before treatment, intakes sit deep, where water is colder and clearer, then drop into massive tunnels. A ultraviolet plant north of the city bathes billions of gallons, disabling microbes without chemicals. Multiple systems interlock, so one line can rest while another carries the load. Aqueducts need downtime. Redundancy is the difference between a hiccup and a crisis. Managers watch rain, snowpack, and demand, balancing storage against floods downstream. Each inch is strategy. Too low risk shortage. Too high risks overflow. The older Croton system still feeds parts of the city, a veteran now backed by younger muscle. In the dark, the mountains send a river of life to the lights. That same network feeds kitchens and fire hoses, domestic comfort and emergency force. Now descend to the other river, steel moving people under the streets. New York's subway is a city beneath the city, 472 stations linked by hundreds of miles of track. At peaks, trains arrive every 2 to 3 minutes on the busiest lines. Signals once used fixed blocks. Green means go, red means stop. Simple, safe, but limiting. Modern lines add CBTC. Trains talk to the track, shrinking headways and boosting capacity. Tunnels breathe and drain. Fans push smoke out. Sumps pull water down and away. Maintenance windows are surgical. Overnight track, signals, and power checks keep the machine ticking. Old relay brains still click beside new software. Redundancy by generation. Stations are pressure valves. Wide stairs, new elevators, clearer wayfinding, reduced dwell time. Passengers are particles. Wider doors and level floors, speed exchange. The payoff is staggering. Millions of rides per day, most of them under a river. And beside these rails, another network hisses. Steam. It heats towers, sterilizes hospitals, and sometimes fogs entire blocks. Open the vault and meet invisible fire. Consolidated steam plants boil water into high-pressure heat for much of Manhattan. Pipes carry it like arteries, buildings tap in with heat exchangers. Insulation keeps energy in, and people safe from the heat below. Hospitals love steam, instant, reliable, and clean for sterilization. Buildings swap steam heat into hot water and air, no combustion on site. Those orange stacks vent and dry lines during maintenance. Safety first. Steam traps are pressure cooker valves, letting condensate out while keeping energy in. Leaks waste energy and can be dangerous, so crews scan for hot spots constantly. On cold mornings, you can see the system breathe. Pressure must stay in a narrow band. Too low, no heat. Too high, risk. Heat is only half the story. The other half is electrons. Keeping the lights on here is a feat of constant balance. Enter the grid. Power arrives from upstate and neighboring states through high-voltage lines. Substations step it down, like gears, so neighborhoods can safely use it. In Manhattan, cables go underground, safer, dense, harder to cool. Transformers are heat managers. Move power, shed heat, repeat. Demand swells with heat waves. Operators forecast every hour and spin reserves on standby. Skyscrapers gulp power. Elevators, HVAC, data. So efficiency upgrades pay citywide. Smarter lighting and controls shave megawatts without anyone noticing. Batteries now buffer peaks. Instant help while slower plants ramp. Network protectors isolate faults fast so one spark doesn't darken a borough. At night, the island becomes a circuit board of human intent. Electricity made vertical cities possible. Now vertical needs its own tricks. How do towers stand so tall in the wind, with hidden counterweights and clever bones? Skyscrapers are bridges turned upright. Steel and concrete carrying loads down to rock. A stiff spine, the core, links to perimeter columns with outriggers like ribs. Architects round corners and notch facades to break up wind vortices. A damper is a silent dance partner, out of phase to calm the sway you'd otherwise feel. Regenerative elevators turn descent into electricity, tiny brakes for the grid, standpipes and sprinklers stack vertically, pumps and tanks ensure pressure to the top. Facades are raincoats and sunglasses, keep water out, glare down, and heat in balance. Even cleaning is engineered, tracks, anchors, and rescue plans baked in. Prefabricated parts snap together like a vertical assembly line. Mechanical floors are lungs and hearts. Air handlers, chillers, and risers moving life through the stack. But towers need connectors. Bridges taught New York to leap water with wire and stone, and tunnels taught it to breathe underwater. Suspension bridges hang roadways from catenary curves, steel cables holding a smile of stone. Foundations were sunk in pressurized boxes, men working on river bottoms in air. Each main cable is hundreds of thousands of wires, redundancy by design. The Verrazzano spans almost 2 kilometers, built with expansion for temperature and wind. Road tunnels breathe with giant fans, fresh air in, exhaust out, so engines don't choke drivers. Underwater, rings of concrete and steel resist pressure. Crews stop leaks like doctors closing veins. Ferries add flex, waterways become backup roads that scale fast. Inspections are relentless, paint, bolts, bearings. Tiny fixes prevent big failures. Spans are pulses, each lane a beat in the city's heart, and in the middle of all this, an intentional void. Central Park looks like leisure. It is also infrastructure, a pressure relief valve for bodies and for storms. Central Park was designed as a lung, clean air, open space, mental health at city scale. Curved paths for escape, transverse roads hidden below to keep traffic out of sight. Traffic moves, people don't see it. Both win. The reservoir once stored city water. Today it balances flows and offers redundancy routes. Lawns and soils are sponges. Stormwater is slowed, filtered, and sent to drains gently. Psychological infrastructure matters. Parks reduce stress and heat, boosting resilience. Tree canopies can cool neighborhoods by several degrees on hot days. Arches and culverts quietly shepherd water. Stone channels guiding storms to sewers. A deliberate pause in a city of noise. Pause over. Back to the unglamorous waste. Every day the city moves thousands of tons of trash, on time, rain or shine. Much of it moves by barge and rail, keeping trucks off jammed roads. Waste out, food in, another silent choreography. Sanitation runs like transit, routes, schedules, coverage. Crews thread impossible spaces with inches to spare. Compactors densify, more tonnage per trip means fewer trucks. Organics programs turn food scraps into energy and soil. Microbes eat leftovers, making biogas that helps power treatment. Sewers collect stormwater and wastewater. Giant pipes slope to treatment plants. Sand and grit drop first, then microbes again polish the water. Before release, light or chlorine knocks out what's left. Exported waste rides rail to distant landfills. Fewer tailpipes here. By dawn, the curb resets. Room for deliveries and walkers again. Which matters, because food arrives while you sleep. A city this size eats like a nation. How do you feed millions every day on time? Hunts Point in the Bronx is one of the world's largest food hubs. Cold chains keep fruit crisp from field to fork. Every box is tracked. Time, temperature, destination. Food rides rail, trucks, ships and planes. Redundancy, so shelves don't go bare. The last mile is the hardest. Curb windows and hand trucks do the final ballet. Thousands of small stores rely on precise timing. Miss a slot, miss a day of sales. Much of the region's food and goods land here, the East Coast's busiest port complex. High-value perishables fly. Hours matter for freshness and safety. When weather hits, routes reshuffle. Algorithms and dispatchers keep breakfast on time. Airports and ports are the city's external organs. They don't just move people, they feed the machine that feeds you. What lands here powers everything from hospitals to bodegas. And when it goes wrong, response time is life. LaGuardia moves short-haul traffic. JFK handles the long arcs of the globe. Airspace here is a 3D puzzle, lanes layered by altitude and direction. Winter adds steps. De-icing is both chemistry and choreography. At the port, tugs and pilots thread ships to berths with meters to spare. Security scans and clears cargo at speed. Risk down, flow up. Automation stacks boxes by algorithm. Shorter dwell means cheaper goods. Fuel moves by pipeline to tanks. Redundant pumps keep runways fed. Perishables and parts fly out as fast as they arrive. Turn times are survival. Human skill still anchors the system. One mistake can stall a region. Back on land, emergency services bend the grid to make space for seconds. Fire, police, EMS, distributed, drilled, and data-driven. Calls triage, units dispatch, intersections change, citywide choreography for crisis, but the city's biggest emergencies are getting wetter. Preemption flips signals to green, an electronic parting of the sea. Aerial eyes guide ground units through canyons and crowds. Hospitals stage capacity during surges. Beds, oxygen, staff flows. The emergency nerve center fuses weather, transit, power and health into one picture. On the water, fireboats bring pumps the size of buildings. Specialized teams practice failure so real failure doesn't win. Alerts now ride the same networks as your messages. Reach beats rumor. Under streets, drills teach muscle memory. Find exits, move air, clear trains. Rising water is the slow emergency that moves fast at the end, so the city is building armor. Protect, absorb, and retreat where needed. 3 tools, 1 goal, survive. Tides and surges are measured, modeled, and messaged. The ocean asks hard questions next. Dunes, berms, and seawalls blunt waves before they reach homes. Wetlands are shock absorbers, slowing water and trapping sediment. Where water must be blocked, barriers swing and slot into place. Tide gates act like one-way doors. Let rain out, keep the river from pushing in. Buildings armor ground floors. Mechanicals move upstairs, panels seal doors. On sunny days, plan for storms. Bioswales sip and slow street runoff. Some proposals imagine harbor-wide gates, but trade, ecology and cost make them complex. Pumps lift water when gravity can't, especially during high tides. Homes add one-way valves to keep sewers from reversing into living rooms. Storms will grow stronger. Design has to grow smarter. By mid-century, higher seas will raise the baseline risk. So parks lift, edges soften, and streets store water briefly before release. Adaptation is the new normal. So what does the future machine look like? Sunny day flooding hints at tomorrow's baseline. Heat waves strain people and power. Shade and cool roofs save lives. Digital dependency means cooling and backup power are as critical as water. Grid hardening, stronger poles outside, sealed vaults inside, reduces outages. Transit seals entrances and vents, keeping tunnels dry is survival. Critical hubs add redundancy, generators, fuel, multiple suppliers. Networks of care are infrastructure too. People keep people alive. New power sources, offshore wind and solar, shift electrons closer to home. Buses electrify quietly, less pollution, less heat on summer streets. Storage smooths intermittency, like a reservoir for electricity. Design pivots from resisting nature to working with it. Small acts scale when you multiply them by 1,000,000. The future feels invisible until you trace the lines. Redundancy gets real: new tunnels, new valves, new monitors, shared corridors reduce future digs, fix once, service many, microgrids island in crises, critical loads stay on, price the scarce, street space, so buses and deliveries move more people and goods with less pain, move more humans per lane, bikes and buses are throughput machines, universal access isn't optional, elevators and wider gates unlock the network, roofs work double shifts, food, power and cooler air, smaller, cleaner delivery fleets slip where trucks jam, a living model tests storms, outages, and traffic before they happen, democracy as infrastructure, plans work when neighbors own them, this place survives by planning for the worst and practicing the everyday. Here's the secret most never see. New York's greatest landmark isn't a skyscraper, it's the vast invisible infrastructure beneath the city that quietly keeps millions of people alive every single day. Harbor, rivers, bedrock, a grid, and the hidden machine, the logic that started with wind and water now runs on code and current. Every step is supported by systems you rarely notice. A million quiet tasks, perfectly timed, keep the promise alive. Design plus discipline equals reliability. From mountain rain to harbor steel, the chain holds, and when we need it most, the system flexes and delivers. Even rest here is engineered, even heat here has a map, even the street hums because something moves beneath. A living organism built from stone, steel, and intention. You feel it when it fails, you forget it when it works. Now that you've seen it, you can't unsee it, the city that keeps you alive every single day.